Hello guys, so today we're going to be solving this indefinite integral. So to first start off, we have to complete this to its square. And to do that, we have to divide the middle coefficient, or the x coefficient, by 2 and then square it. So 4 divided by 2 is 2, 2 squared is plus 4. So plus 4 minus 4. This is of course the same as writing this same expression we had earlier on. So x squared plus 4x plus 4 is a perfect square, namely x plus 2 squared. So we can rewrite this as x plus 2 squared, like this. And of course there's a plus 5 and minus 4, which become plus 1. And all of this is of course inside the square root, otherwise we wouldn't even be doing this. So x plus 2, we can use trig sub over here. So x plus 2 will equal tangent theta. So dx will equal secant squared theta d theta. The reason we use tangent theta is because of this famous identity, namely tangent squared theta plus 1 is equal to secant squared theta. So if we substitute tangent theta instead of x plus 2, we end up with tan squared theta plus 1. And that is the same as this identity, which is equal to secant squared theta. And the square root of secant squared theta is just secant theta. Dx, however, is equal to secant squared theta d theta. Now the next step is to do integration by parts. Now how will we do integration by parts with such a weird looking integral? Well, it is weird, yes, because there is two trig functions, and to do integration by parts, we need different types of functions. So how will we do it? Well, basically, you have to think of which one is easier to differentiate and which one is easier to integrate. So is secant squared theta easier to integrate or easier to differentiate? In my opinion, it's easier to integrate secant squared theta because it's literally just a derivative of tangent theta. So dv is probably secant squared theta. And u is secant theta in that case. So the derivative of secant theta is secant theta times tangent theta. Like this. And the integral of secant squared theta, as we just mentioned, is tangent theta. So the integral of secant cubed theta d theta is equal to uv, which is secant theta times tangent theta minus the integral of v du, which is tangent theta times secant theta times tangent theta. If we simplify this, we end up with secant theta times tangent squared theta d theta. So recall the trig identity from earlier, which is this identity. If we use this and isolate the tangent squared theta, we end up with secant squared theta minus 1. So if we replace the tangent squared over here with that identity, we end up with the negative integral of secant cubed theta minus the integral of secant theta d theta. like this. And this is, of course, equal to secant cube theta d theta. Like this. So negative times the integral of secant cube theta d theta is just, well, negative of that same integral. We can add the same integral on both sides and end up with 2 integral of secant cube theta d theta, which is equal to secant theta times tangent theta. Minus times minus is equal to positive, so positive integral of secant theta, which is just the ln of the absolute secant theta plus tangent theta. And if we divide both sides by 2, we end up with this as our final result. Of course, there's a plus c at the end. So this is technically our answer, yes, but this is in terms of theta, and we want the answer in terms of x. So what was theta in terms of x? To get back to that, we have to use this identity. I mean substitution we used earlier on. So arctangent of x plus 2 is equal to theta. If we substitute this back into our colossal expression over here, we end up with secant of arctangent x plus 2, secant of arctangent x plus 2 times tangent of arctangent is just the input, so x plus 2 plus the ln of the absolute secant arctangent x plus 2 plus tangent of arctangent is just the input again, so plus x plus 2 absolute, close like that, divided by 2 plus c. So since this is a trig inside of an inverse trig function, like the inverse trig is the input of the trig function, we can simplify this into, well, a simpler expression by constructing a triangle. So let's say arctangent of x plus 2 is theta. This is actually true because we already substituted it. So in that case, x plus 2, if you take the tangent on both sides, you end up with x plus 2 is equal to tangent theta. If you draw a triangle, tangent by definition is opposite over adjacent. So x plus 2 becomes the opposite side, if we say theta is over here, of course. And since x plus 2 is equal to x plus 2 divided by 1, like it's the same thing, 1 is the adjacent side. So the hypotenuse, due to Pythagorean theorem, becomes the square root of x squared plus 4x plus 5. So what we want is secant theta. And secant theta is equal to 1 over cosine of theta. And since cosine of theta, by definition, is adjacent over hypotenuse, if you take the reciprocal of that, you end up with the hypotenuse divided by the adjacent side. So secant, by definition, becomes the hypotenuse over the adjacent side. So if we, use this formula on this triangle we constructed, it becomes the square root of x squared plus 4x plus 5 divided by 1. But I'm not going to write 1 because, well, it's the same thing. So instead of secant arctangent x plus 2, I'm going to be substituting this value. So instead of this and the expression inside the natural log. So the actual answer becomes the square root. If we look at the original answer we have, the actual answer is the square root of x squared plus 4x plus 5 times x plus 2 plus the natural logarithm of the absolute square root x squared plus 4x plus 5 plus x plus 2. All of this divided by 2 plus c. Now this is the actual answer of the indefinite integral of the square root of x squared plus 4x plus 5. Thank you for watching.